Welcome to the CUDA Graphs tutorial in the CUDA training series. Today's presentation will be given by Matt Stack from NVIDIA. So welcome to all the users from Oak Ridge and Argonne and NERSC. So it's going to same as before. It's going to be an hour-long or hour-ish long presentation followed by a set of hands-on exercises based on the topic. If anybody does not have an account, we do have the ability to set up a training account. But I believe that everybody here should have one or should have been emailed instructions for how to set up an account. Not much else. I'll just end the introductions here, and I'll pass it on to Matt.
Awesome, sounds good. Hello, my name is Matt Stack, and I'm a solutions architect at NVIDIA. And today we are going to talk about CUDA Graphs, which is a performance enhancement feature in CUDA, and we will be focused on the basics. This talk will hopefully be beneficial to anyone who has not experimented with CUDA Graphs yet, or maybe if you heard about it back when it was introduced in CUDA 10 and would like a refresher. And before we begin, just to note that this is a relatively advanced CUDA topic, so we are really going to focus on the core idea and introduce the graph way of thinking about CUDA operations, rather than trying to jam it all with the newest features. And please feel free to utilize the chat and ask questions as we go along. We have Max and Robbie here with me from NVIDIA to help answer questions as they come up, and we can address some at the end as well. Today, we would like to ask the question, what is CUDA Graphs, and how can they be a useful tool in the toolbox of a CUDA programmer? And to set the stage a bit, CUDA kernels over the years have been getting faster and faster, thanks to newer hardware and improved software. And launching any CUDA operation from the CPU incurs what is commonly known as the launch latency overhead. And the launch latency overhead can be defined in a number of ways. But the one I like to use is the time between the start of the launch API call and the start of the kernel on the GPU. While kernels have been getting faster, it's possible now more than ever to have kernels that run the same amount of time as the actual overhead itself. And when you have these kernels with runtime that is sufficiently short, if they are around the same time or less than the launch overhead, this launch overhead will actually dominate the overall time of launching and running. And this pattern can be improved by using CUDA Graphs. Okay, a graph is a series of operations connected by dependencies that is defined separately from its execution. And all CUDA work creates a graph in the traditional sense. Say with a really basic CUDA code, you have 3 kernel launches into the default stream. That is 3 nodes connected by the implicit dependency of the stream ordering, almost down in a line. And we can see from the left that using CUDA streams creates this directed acyclic graph of execution that is perfect to visualize how a CUDA graph is formed and that the execution capabilities are the same. And from left to right, we are converting this CUDA work into a graph that has nodes and dependencies, and we will talk about that through this presentation. The nodes that make up a CUDA graph are any asynchronous CUDA operation. It is important to note that these operations don't have to all just be kernels. They can be memcopies and memsets or CPU callback functions or anything you could put into a stream. This is deviating a bit from the intro level material, but you can use the new stream ordered memory allocators with CUDA graphs. And in the end of the slides, there's a link to learn more about that if you're interested. We're not going to touch on that in this presentation. And looking at the dependencies between nodes, just going back for 1 second, They can be either implicitly ordered by the sequential execution of the operations in a stream, or there can be explicit dependencies from CUDA wait and signal events. As you can see, it maps from left to right. And you can also have subgraphs, which we will talk about in a few slides. Going back to the idea that CUDA graphs can be generated once and then launched repeatedly, thanks to it being defined separately from its execution, this repeated execution is the big deal here. We are allowed to pay the setup cost of the graph, which we will talk about in a few more slides, only once, and a single execute operation to start the whole graph off, which can be very complex. This is just a few nodes here on the slide, but it could be any number of nodes. I don't think it's an unlimited amount of nodes, but a very large amount of nodes, and it can be very complex with its dependencies. And when we were looking at the corresponding stream work from before, the big difference is that launching was more piecemeal, which is one at a time, and then only runs once. The stream and its work were consumed and to be reissued in its entirety if you wish to relaunch it. And latency hiding here is the key point, as with all GPU computing, and relaunching the graph many, many times is where you will start collecting very useful CPU time back. Here we can see on the bottom how launching a graph with a single operation implicitly kicks off a number of operations that we created when while allowing the CPU to remain open for other work. You can see the CPU is idle. And contrasted to the stream example above, where the CUDA kernel launches are more piecemeal, and the CPU can be quite busy actually launching the work. This example is not to any particular scale and shows that if your kernel execution time is longer than the launch overhead by a bit, you can still benefit from the freed CPU resources. And here we see a similar example, again, not to any particular scale, that I like to think highlights the other case where your kernels are very small, smaller than the launch overhead. And we have the GPU actually waiting idle for the CPU to launch the work. They will each have to wait for the CPU to finish that previous launch before they themselves can get launched, resulting in this spaced pattern you can see in Nsight systems if you are profiling that is letting the GPU be idle for that time. And as mentioned before, when the kernel runtime is short, the total execution time is dominated by the CPU launch overhead. And launch overhead is generally a few microseconds. And I personally wouldn't worry explicitly if the kernel times are exactly equal or exactly less than, just because it could be a number of microseconds, or it could be a dozen, depending on what you're launching. But these kernels we are talking about are generally in the range of a few microseconds. And also just noting that using CUDA graphs doesn't actually affect the pure runtime performance of a kernel once it's on the GPU. We're more targeting the combined launch cost for a program and how that decreases. CUDA Graphs has a 3-stage execution model where we define, instantiate, and then execute into a stream. And on the left, the define stage is what we will see in the coming slides with examples, where we tell CUDA, okay, these are the nodes, the parameters, the dependencies, which GPU to target, which stream to launch to, and so forth. And we are really defining the structure and the contents of the graph. And then we instantiate the graph, which is two different types, which we will see in the examples and the homework at the end. And when we instantiate the graph, this is similar in performance cost to launching the kernels directly into the CUDA stream, but you only need to pay that one time. And then we can execute the graph many, many times, effectively hiding that setup cost. And that is where you can see overall, although you are doing this one heavy cost, the more you relaunch the graph, the more you are saving from that reduced overhead. We mentioned before that stream launches set up and launch per operation, letting you change the parameters and organization each time freely. And this is your typical way to launch CUDA code or to launch CUDA operations, as you've seen many, many times before. Because we are focused on only really reusing that same graph that we paid a relatively high setup cost for, we are able to, of course, relaunch on the condition it stays the same with neither the parameters and the topology changes. And the instantiation phase is the most expensive setup, where we are doing the work to set up the graph. So we typically tend not to try to instantiate too much, just because then you're sort of defeating the purpose of CUDA Graph. The cost is not disappearing by magic, but if we can reuse that same executable instance we have, then we are getting that CUDA work launched to the GPU for pretty cheap compared to the piecemeal stream launch. And that would be the ideal case on the right side, but often not 100% applicable all the time, as codes have branching paths and changing parameters, etc. And in the middle, we have graph update, which is a set of API calls defined in CUDA, in the CUDA docs, which is linked at the end, and I'm sure you could find online, that allows you to make the changes to the graph with some conditions to maintain a level of performance. For a more detailed explanation on this, an example, I recommend the GTC talk called Effortless CUDA Graphs from the most previous GTC. It walks through the details of creating a CUDA graph setup that is performant, giving a real world code example. The presenter uses a finance code that they came across and saw that the kernels were pretty small and being run one after another. And they go through the steps of identifying places where you can use CUDA graphs, and there are a number of tricks you can do to introduce CUDA graphs efficiently, even if the execution graph is not 100% the same all the time. And that talk is linked at the end of the slides as well. And on a similar note, another example I saw recently in the same vein was from an FFT code. CUDA Graphs was introduced with relatively small code change. Really only 3 extra key lines were added, and they saw about a 12% performance boost. But this was a toyish example, but the basics are still there, whether it's a small FFT example or a big particle physics code, just defining your CUDA operations as a graph. So we covered a lot there, so I'll just pause for a minute and check any of the questions. Max, were there any questions that came up that you wanted to point out, or do you want to wait until the end, or we could keep going?
No, you can keep going.
Okay, sounds good. Okay, there are 2 ways to define CUDA graphs, and the first one we will look at is called stream capture. And stream capture it does what the name sounds like. you record the operations of a stream without actually launching any work to the GPU. And afterwards, when you finish capturing, that graph object is ready to be instantiated. And all the nodes and dependencies are already defined for you by CUDA. This is a very easy way to introduce CUDA graphs into your code. And it was the way that FFT code did it with just a few line changes, because it requires very little code change compared to the explicit graph creation that we will see in a bit, which is the other method of defining a CUDA graph. Stream capture is also very useful when you have a library call, such as a general matrix multiply call to cuBLAS or any call to cuFFT, because most of the time we as users don't actually know the specifics of what work is getting launched behind the level of abstraction given to us by the library and with what parameters and so on to achieve that result. So stream capture is real helpful because it will handle that for you. And just a note at the bottom that CUDA stream sync will cause issues for you if your library call calls it, because the capture is not actually launching anything. But CUDA Graphs is a few years old. It came out in CUDA 10, or it was introduced rather in CUDA 10. So I would imagine most mainstream libraries would have graph capabilities. And if you try to capture with a CUDA stream sync, you'll get a runtime error. So looking here at our first example code, we are using stream capture to create a graph from the work in the streams. And we start by using CUDA stream begin capture and pass that stream1 as an argument. And then we use our familiar stream kernel launch API as usual, going through, and then at the end, we convert it into a graph. Although just to keep in mind, we are still doing the define stage here. When we CUDA stream and capture, we just have a graph object that is ready to be instantiated. And also note here that while we are only capturing stream1, CUDA is still able to pick up on the event record to wait event dependency and the following node, as you can see on the picture on the right, node C in a different stream. And the resulting graph is what we expected, which is great. And also note that not every operation makes sense in a graph, as we mentioned in the last slide, like CUDA stream sync, because it just doesn't really mean much anymore in this deferred model, and you'll get an error. This is an example of capturing that library call with stream capture, as we talked about before, and that resulting graph, because the library call could be one kernel, 5 kernels with however many dependencies, mem copies, etc., is fit into that resulting graph, as you can see from the picture on the right. And we use the exact same syntax as we did before to capture that stream, and the resulting graph is what we expect. Okay, so this is the second method, creating the graph directly. Is that other method for the define stage. And before, when we looked at the stream capture method, we had CUDA we had stream capture actually paint the picture for us. And now we can directly take charge and create the nodes and create the dependencies ourselves. And you can kind of tell on the right with the code here that this requires more code change, but it does have the benefit of giving you more control. And along the same line, it also usually requires a deep knowledge of the code and all the code paths and possible combinations of operations and arguments. But some do find this easier than using the stream event syntax. But that is up to you, and the full list of API calls is in the CUDA docs again. It can get pretty extensive, and more are added with each iteration of the CUDA toolkit. And you can see that, unlike with stream capture, it's a little bit harder to just glance at the code and know what we are getting. But there's an example of this explicit graph creation in the examples at the end, if you want to give it a go and get a feel for it. This is the same example as before, but you can see that we are showing that you can choose when to use stream capture and when to use the explicit graph creation, how it works best for you. And the resulting graph object can be from a combination of both. Here we use stream capture for the library call because that makes a lot of sense. And we already had an explicit graph going, and we can explicitly add it as a child graph node and fit it right into that graph. And this just shows that work is ordered between stream operations, just as for normal CUDA. And a graph is just another launchable type of work if you launch it into the stream, as you can see on the right. However, small caveat, graphs do ignore the stream serialization rule, and the launch stream is used only for ordering of work before and after. With the picture, there are some slightly different colored nodes. Maybe the green one may run on GPU 0 and the blue may run on GPU 1 with different streams concurrently. So what can you not do with CUDA graphs? As with other CUDA work, CUDA graphs will not automatically place nodes on different devices for you that you have available without you explicitly telling it to do so. Say we have independent nodes B and C and 2 GPU at our disposal. The best choice is really only known to the programmer, which has to do with data locality usually. So CUDA doesn't attempt to make that choice to auto assign for you. Maybe you are spread across a few GPU because you have a lot of data, but you're still using small kernels. Then you can decide in the creation of the graph and the nodes where the operations will run. And that choice, again, is up to you. Graphs won't explicitly handle it. You'll need to cycle that set CUDA device to actually launch into the other devices. This is a bit more on the theoretical side, but just to note it, CUDA has chosen the execution dependencies method of defining graphs rather than a data dependent view, just because while both are directed acyclic graphs, the execution dependencies method is more general and more future-proof for future features that have been added, such as that stream-ordered memory allocations. And execution dependencies is the superset, which can be used to define any data-dependent flow and more. And so what can you do with CUDA graphs? You can do rapid reissue of work. That's the big thing here. For the right type of workload, graphs can improve the overhead costs associated with launching work to the GPU. And while the initial cost is large, it's only once. And therefore you continuously save on overhead the more you launch it. And CUDA graphs are heterogeneous types. So you can include GPU work and CPU work and data movement with your graph. And one of the benefits of defining your operations into this single cohesive group of work is that CUDA can apply some subtle optimizations that it couldn't if it only saw each kernel as they happened, and you can give it more of the full picture. And CUDA is closest to the operating system and the hardware, so it can sync across multi-GPUs as well. Won't touch on this too much, but just to let you know that it is there. So this is actually a slide that we saw in the beginning. And we are looking to reduce system overhead around launching short-running kernels. And hopefully this slide makes a bit more sense now than it did when we first saw it from the examples and the actual code and API. So CUDA Graphs has seen a bunch of new improvements and features since CUDA 10, and I didn't specifically touch on any of them in this intro. And they are linked at the end of the slides here, just a few of them. And for takeaways, I do kind of like to think about like the economy of scale with a code. Say if your kernels are really long and they take a really long time, then launch latency is just a very tiny amount of that total execution time. So your programming time might be better spent exploring other operations, or sorry, not other operations, other performance options. And the kernels themselves are not getting faster, but the overhead is reduced because we are defining that work only once and then executing it many, many times. And just to state the definition again, because I find it helpful, a graph is a series of operations, include but not limited to kernel launches that are connected by dependencies and are defined separately from its execution. And a big focus is on the overhead cost regarding launching small kernels and how they decrease. And as I mentioned before, CUDA Graphs have seen a number of improvements since CUDA 10. And while I didn't specifically mention them, you can find a lot of them if you read the what's new in CUDA version blank 11.4, 11.5 on the CUDA developer blog website. Usually you'll see a mention to a new feature in CUDA Graphs in there, which is really cool. And that takes us to the end of the presentation. This is for some further study, and the slides will be available after the talk. And we also have the homework if you want to stick around and give it a try. I think we have 2 examples. Yep, any questions? Max, were there any that you wanted to point out that came through? Or Bob?
And if anybody wants to unmute and ask questions, feel free to do so.
There's one that came in about whether or not a graph can be cyclic or does it have to be acyclic. I don't know if you want to respond to that. I was typing something up, but it might be better to address it live. Can a CUDA graph be a loop itself, and it can conditionally exit?
I believe it does need to be acyclic. I have never experienced a looping CUDA graph in of itself. Was that what you were gonna type in the chat, Bob?
Yeah, I was going to say that as far as I know, CUDA graphs are intended to capture acyclic graphs, not cyclic behavior. And the question is about whether or not it can be done or not is a separate question, in my opinion. And I don't really know the answer to that. Right now, I'm sort of struggling to think about how you would construct a cyclic graph to begin with. You know, a graph is essentially an ordered sequence of, as Matt described, an ordered sequence of nodes of certain types. And certainly a kernel cannot affect exiting behavior of the graph by itself. A memcopy node cannot affect exiting behavior of a graph by itself. And so I'm left with the host node, and I'm not sure that there is any way to express a conditional dependency, which is what you'd need, right? A host node would essentially have to have two different arrows coming out of it, or some kind of node would have to have two different arrows coming out of it. So I guess I'd have to spend some more time thinking about that last question. I don't really know if it's possible to express a graph that has a conditional exit.
All right, does anybody else have any questions that they would like to ask live? Oh, one just came in. When a graph is captured, aren't we capture the expanded form of the loop or a condition? I'm not sure if you get that. We can ask for clarification.
When a graph is captured. Oh, so we don't capture a whole.
Ulsan, so if you, oh, sorry, go ahead.
Yeah, no worries. Yeah, I think usually we do that launch operation in a loop. And then I think it was one of the previous slides, you could kind of see it, that it's like ordered via that launch stream. So it's just like another type of work you would launch with CUDA, like any kernel launch. It's the same idea there. If that answers the question.
You could certainly create at least the launch creation, sorry, the graph creation. Let's talk about the graph capture via API, because I think, to me anyway, it makes more sense. We're using the API method for graph capture. It's at least syntactically possible to express a loop. Having said that, I don't know what would happen if at that point, if you did express a loop. Expressing a loop would be fairly simple, right? You just have, every time you instantiate a node, you create dependencies, right? And so the dependencies determine what's going to happen after that node completes. So it would simply be a matter of looping the dependencies, so that if you had node, node A, for example, has a dependency, or sorry, node B has a dependency on node A. Node C has a dependency on node B. And node C has a dependency on C. That wouldn't make sense. Yeah, I'm just not sure that it's possible to express a loop, or more importantly, to express conditional dependency. I'm not sure that either of those are possible. So for the time being, without someone proving me wrong or identifying some arcane way to do it, I'm going to suggest that graphs, CUDA graphs, are intended to collect acyclic behavior that has essentially a defined starting and ending point. It's not obvious to me that these questions about loops or conditional behavior of dependencies or conditionally exiting a loop are even achievable or realizable syntactically. And I'm quite certain that's not the intent of a CUDA graph. Certainly a loop is not the intent, because a loop basically is going to suggest infinite behavior, and there's no intention of that with CUDA graphs. If you did want to have some sort of behavior like that, my basic suggestion would be to use all of the acyclic work that you wanted to do and capture that in a graph, and then use an overarching host code executive that launches that graph and then makes the conditional decisions about whether or not to launch the graph again and again. That would be my suggestion.
Hey, Matt, this is Hey. I have a question. I guess I'm wondering if there's a downside. Like if I were to profile my code and identify a region that has, a bunch of kernel launches, that happens multiple times, is that enough to say like, oh, I should try CUDA graphs on it? Or are there other considerations I should be thinking about before applying it to a particular region? Are there other trade-offs that I should be thinking about?
Yeah, that's a good question. And it reminds me a lot of the example that the presenter in the GTC talk went through. I don't think there's, Yeah, I would say if you profile with Insight Systems and you see that there are a number of things that could catch your eye, like that spaced pattern that we saw, where the GPU is actually waiting for that CPU to send it the next work, just because the kernels are happening so fast. I would think that would be a good measure. I don't think
I would look at the principles that Matt expressed as motivating principles for use of graphs, or maybe if we went back and looked at the execution behavior slides. The basic idea is that graphs, from a performance perspective, graphs can improve the performance when the host side scheduling of work, that's typically CUDA kernels, but there might be other types of work scheduling like asynchronous memory copies and things of that nature. So I'm lumping all that together and saying the host side scheduling of work is a significant factor for performance. So in the trivially simple case, we have a very small kernel that we're calling perhaps over and over again. Or maybe even a bunch of very small kernels that we're calling over and over again. And what we observe when we do our profiling is that the kernel's running for a few microseconds, and we're witnessing also a few microseconds of launch overhead. And as a result of that, the rate at which that I can issue kernels is throttled to approximately half of the rate that I would desire. That, to me, that sort of profiling analysis of your code would be one of the key motivators to consider whether or not graphs can improve the performance. As I mentioned in one of my comments, graphs can also be thought of from the standpoint of modular coding as a way to modularize code and also to abstract or express relationships more clearly. That's perhaps a little bit debatable. You know, beauty is in the eye of the beholder, but certainly graphs represent a novel method for expression of workflow. So those are some ancillary benefits, but they're not necessarily related to performance at all. The key performance benefit is going to be when you profile your code and you observe that there's significant gaps in your profiler timeline between the work that you would like to issue. And especially when the work that you would like to issue consists of relatively small chunks of work. Definition of small here is things that don't saturate the GPU. Then that might be one of the key things that I would look for when considering whether or not graphs could significantly improve the performance of my code.
All right. Does anyone else have any other questions or follow-ups? Right. Going once, going twice. Okay. So, I believe that brings us to the end of the webinar portion.